Welcome, math friends. We are working with trigonometric equations today. We will be dealing with predominantly sine, cosine, and tangent. We will deal with inverse trigonometric functions later. But for today, we are going to be using the unit circle. We'll be solving within 2 pi from 0 to 2 pi. If you were to solve over the entire domain, you would have some sort of integer n where you would say n pi or n pi plus 2, depending on it's going to happen at every 2 pi from that value. I will show you what I mean with the first problem. When you are solving trigonometric equations, the goal is to get a trigonometric function by itself equal to some value, and then you find that value on the unit circle. We are going to use a zero product property whenever we have a factored expression in the equation. And we're going to use the unit circle to determine where the simplified equation is true. So we might need to simplify down, which we will do in a few. The first problem that we have will not need to be simplified. We'll just need to get a single sign rather than a sign squared. So whenever you have powers, obviously you're going to use roots to get down to a single power. Here we go. We're going to solve for the angle theta, where theta is between 0 to 2 pi. Sine squared of theta is equal to 3/4. What I'm going to do is I'm going to square root both sides to get just sine of theta. That means that the sine of theta is going to be equal to the square root plus or minus of 3/4. I cannot take the square root of 3, but I can take the square root of 4. That's the same thing as plus or minus the square root of 3 over the square root of 4, using the properties of radicals. Sine of theta is then equal to plus or minus root 3 over 2. Breaking that down, I am looking for an angle where the sine is root 3 over 2 or negative root 3 over 2. Recall that sine is the y value in the unit circle. So we need a y to be root 3 over 2, both positive and negative. So looking in the first quadrant, my y is root 3 over 2 right here. So the first solution I have for theta is pi over 3. Moving into the second quadrant, I see positive root 3 over 2 at 2 pi over 3. So I'm noticing that my denominator is 3 here, which means that I've got 60 degrees. And then from the next one is 120, and so on. Into the third quadrant, my y of negative root 3 over 2 is at 4 pi over 3. And then in the fourth quadrant, negative root 3 over 2 is for 5 pi over 3. So for the interval 0 to 2 pi, my solutions, I have 4, are pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. If I was to do this for all values of theta, it would be pi over 3 plus 2 pi n, because it happens every time that I do a full rotation. So another 2 pi is going to give me the same value. So whenever you're solving over an entire domain, you just need to make sure that you are including it for every 2 pi. Moving on to the next equation, I see I have sine squared and cosine squared. What I think I'm going to do here is I'm going to divide both sides by cosine squared so that I can get both of these trigonometric terms on one side of the equation. Sine squared over cosine squared, well, sine over cosine is tangent, so that's going to be tangent squared. And cosine squared divided by cosine squared is 1. Now I can square root tangent and square root 1. That means that my tangent of theta needs to be equal to plus or minus 1. So tangent is y over x. But where am I going to have the y and the x that are the same value, both positive or negative? So I could have a positive and a positive, positive and a negative, negative and a positive, or negative and a negative, whatever combination for y and x. Hopefully you know that that happens at our 45-degree variations. So the first time would be at this pi over 4. Root 2 over 2 divided by root 2 over 2 is 1. So that means that for theta equals pi over 4, I've got my first solution. Root 2 over 2 over negative root 2 over 2 is negative 1. That also works. That means I have a solution of 3 pi over 4. Negative root 2 over negative root 2 over 2 is positive 1, also a solution. And the last one of negative root 2 over root 2 over 2 is negative 1, which is also a solution. So my 4 solutions happen at each of the pi over 4 variations in the first, second, third, and fourth quadrant. Now I have the sine of 2 theta minus cosine of theta. I'm going to use the double angle formula for sine to rewrite sine in terms of cosine. So the sine of 2 theta is going to become the 2 sine of theta cosine of theta. Minus cosine of theta equals 0. Both of these terms have a cosine of theta that I can factor out. That leaves me with 2 sine theta minus 1 equals 0. And then I can use the zero product property to set each of these equal to 0. I'm then looking for the cosine of theta equal to 0 and 2 sine theta minus 1 equal to 0. Cosine theta is good, but the 2 sine theta minus 1, I need to add 1 and divide by 2. That's 2 sine theta equals 1, and sine theta equals 1/2. So in my unit circle, I'm looking for cosine to be 0 and sine to be 1/2. Cosine is x, sine is y. So let's go back up to my unit circle. Where is my x0? That happens here and here at pi over 2 and 3 pi over 2. So theta is going to be equal to pi over 2 and 3 pi over 2. And then where is my y? 1/2. Looking at y, I see a 1/2 here. The next one happens here. And then in the third and fourth quadrant, they're negative. That's not going to work. And so I'm looking at pi over 6 and 5 pi over 6. Pi over 6, pi over 2, 5 pi over 6, and 3 pi over 2 from least to greatest. Let's move on to our last problem of cosine 2 theta plus cosine theta. I cannot factor out a cosine theta here because I don't have cosine squared theta. I have cosine 2 theta. So what I need to do is use the double angle formula for cosine of 2 theta and rewrite that as cosine squared theta minus sine squared theta. Can't really factor anything yet, but maybe I want to rewrite sine squared theta in terms of cosine squared theta. Using the Pythagorean identity of sine squared theta plus cosine squared theta equaling 1, if I subtracted cosine, then the sine squared of theta is equal to 1 minus cosine squared theta. I'm going to substitute that in here, which is going to give me cosine squared theta minus 1 minus cosine squared theta plus cosine theta equal to 0. That negative needs to get distributed. That means I have cosine squared theta plus cosine squared theta minus 1 plus cosine theta equals 0. Cosine squared theta plus cosine squared theta is 2 cosine squared theta plus cosine theta minus 1 equals 0. This is factorable. Think of this in terms of a quadratic. If you had 2x squared plus x minus 1 equals 0, could you factor it? Yes, you can. What multiplies to the AC term, which is negative 2, and adds to the middle term of b, which is 1. That's going to be positive 2 and negative 1. So I can split that middle term of plus cosine theta into 2 cosine theta minus cosine theta. That gives me 2 cosine squared theta plus 2 cosine theta minus cosine theta minus 1 equals 0, and then I can factor by grouping. The first two terms share a 2 cosine theta. That leaves me with cosine theta plus 1 factor out a -1, that's cosine theta plus 1 equals 0. I then have 2 cosine theta minus 1 times cosine theta plus 1 equals 0. And I can use the zero product property, set each of those equal to 0. 2 cosine theta minus 1 equals 0, and cosine theta plus 1 equals 0. Adding 1 to both sides and dividing by 2 gives me cosine theta equal to 1/2. And then subtracting 1 from both sides gives me -1. So where is x 1/2 and where is x -1? Let's go back up to our unit circle. We're looking for 1/2 and -1 for my x term. X is equal to 1/2 here and -1 here and 1/2 here. That means that my solutions are pi over 3, pi, and 5 pi over 3. Some of the operations that I did or the steps that I took in terms of condensing or rewriting might not be intuitive to you. It takes practice. It takes working with the trigonometric identities and looking at evaluating. And maybe sometimes you try something and it didn't work out. That's okay. Erase it and try again. It's just perseverance when you're working with these problems. Thanks for watching. I hope this was helpful.